Algebra 2, welcome back. Here is 7.2. Okay, here's our last section for kind of right now in terms of exponential functions, okay? 7.4, we're going to talk about the other function that we're focusing on for chapter 7. So here's kind of the last little bit about exponential functions, right? We're talking about exponential decay, same idea, graph transformations of it. We're also going to talk about the number e, okay, and you're hearing that right, the number e, and growth and decay functions involving e, okay? So we'll get there, okay? If you're like, is this guy okay? E, a number? Yes, I am saying that right. But for the time being, let's get into exponential decay. And so it has the same general form that we've looked at so far, okay? So same form. Same general form. And if you remember, that was f of x equals a times b to the power of x minus h plus k. Okay, what makes it decay is that our b is going to be between 0 and 1. Okay, and so that's kind of what is the difference here. And so the graph of a decay function, get a little bigger actually. The decay function looks a little bit typically like this. It starts off huge, but then it gets pretty tiny. Okay, so it's like the opposite of our growth function, right? If you remember our growth, it starts off pretty tiny, but then it eventually gets pretty big. Okay, our decay function is the opposite. And so it has some y-intercept and sometimes it has an x-intercept as well. And then it has a horizontal asymptote. Okay, all the information is gonna be pretty much the same aside from the b and the overall shape of the graph. Okay, so we have a few things to identify here. All right, our A, H, and K are all going to stay the same. I'm not going to write them down because you should remember them. I'll say them though. Our A is our vertical shrink or stretch, right? Our H is our horizontal translation, and our K is our vertical translation. All right. And then remember, we have a horizontal asymptote. I will write that down because this is new information. Our horizontal asymptote is going to be y equals k. New information pertaining to this chapter, right? And then same idea for the domain and the range. Domain will still always be negative infinity to infinity. And then our range varies. It's going to change depending on the function. Okay. All right, let's just do some examples, okay? So start by describing the transformations in f of x equals 3 times 1/2 to the power of x plus 1 minus 2. Sketch a graph, labeling the intercepts and horizontal asymptote, and then state the domain and range. Okay, so let's identify our A, H, and K here. I'm gonna rewrite the function. Okay, notice that this is the K, we can tell right away because our base, B, is 1/2, and 1/2 is definitely between 0 and 1. Okay, and so A in this case is 3, H is -1, and K is -2. What do each of these do? Okay, A equals 3, that's a vertical stretch, right? Vertical stretch by 3. -1, that is a shift to the left because it's negative by 1. And then shift down by 2. Okay, we know our horizontal asymptote is our k, so y is equal to -2. And then now let's go ahead and graph this to see what our sketch will look like. So I'm going to share my screen onto Desmos. And so let's type this in. We have 3 left parenthesis 1 divided by 2 go out, use the right arrow key to leave the denominator right, parenthesis, a to the b. We're going to need left parenthesis to make sure our x plus 1 stays in the exponent. And then leave the exponent using this right arrow key, minus 2. All right, here's our graph, and then I can quickly graph this horizontal asymptote y is equal to -2. And I can make this dotted. Cool, so there's our graph. And so here are our intercepts. Okay, we have a nice one at a y-intercept at 0, -0.5, and then an x-intercept at -0.415, 0. Okay, so let's go ahead and graph this. All right, we have that decay shape. It's starting big and then getting small and staying along the asymptote. So, boom. Draw myself a nice pair of axes. Or a somewhat nice pair of axes, as best as I can make them look. Okay, those are not terrible actually. And so then I'll do my ticks. I'll scale these by 1. Looks like we don't need to go that far up or down. Okay, 1, 2, 3. -1, -2, -3. 1, 2, 3. Okay, we'll draw our horizontal asymptote first. Here at y is equal to -2. And then we have some asymptotes. Forgot to write those down really quick, but we have an x-intercept. Did I just say asymptote? I meant intercept. We had an x-intercept at -0.415, 0, and then a y-intercept at 0, -0.5. All right, so -0.5 is right here-ish, and -0.415 is like right here, kind of as best as we can, right? And then we know it's kind of shooting down. Boom, boom, and then it kind of tapers off and joins its friend, the asymptote, as they go to the right. Okay, and so there's our graph. We'll label our points. This was -0.415, 0, and this one was 0, -0.5. Oh, and then we need to label our asymptote. Y is equal to -2. Cool, and then lastly, domain and range. Domain never changes for the exponential function. The range, in this case, the smallest we go is -2, and then we go upward. So we start at -2, not touching it though, because there is an asymptote, so parentheses, and then off to infinity. Cool. All right, we're not going to do another one of that, just because we did 2 examples in 7.1, and it's the same idea, right? We pretty much did the exact same thing from 7.1. We were just dealing with a different base. And we'll do that actually one more time, but now involving the number e. Okay, so let's talk about e really quick. What is going on with e? So think about, do you guys remember pi? Okay, pi, I don't know a whole lot of digits. I know it's 3.1415, I think, etc. After that. It's just like pi. Pi is actually a letter. It's a Greek letter. Okay, so e is also kind of the same idea. It's equal to a pretty interesting number, okay? So some facts about e, it's called the Euler number. Okay, that's why it's abbreviated e, called the Euler. Euler was a mathematician. That's how you spell and pronounce his name. Okay, called the Euler number. Okay, and it's an irrational number, meaning that it doesn't terminate and it doesn't repeat itself, like for the rest of the number. It's not a it does repeat in some parts, but not forever. And so that's kind of like pi in that regard. Pi is also an irrational number. Where does it come from? Okay, it comes from this little formula, comes from 1 plus 1 over n to the nth power. Okay, when you take this formula and you plug in huge numbers of n, the bigger you get, the closer to e it's going to be. So it comes from this when n gets huge. Okay, and then lastly, what is the value of e? It's about 2.71828 1828, and then it keeps going after that, right? So it repeats in some parts, but when you keep going in the number, it stops repeating itself, right? And so there's the need to know information about E. So the bigger I plug in N, so if I plug in 1,000, 10,000, 100,000, a million, a billion, a trillion, etc., the bigger it gets, the result is going to get really close to this number. And you can try it out yourself if you're curious, right? And so that's E. And so E kind of happens a lot in nature, okay? It's going to be a big part of what we talk about in 7.4 and 7.5 and 7.6. But for now, it's also used in exponential functions as the base. You're going to see it really often as a base, okay? Now here, E is always 2.718281828, etc. It's not going to change in value. E is E. And so it might seem like it's always exponential growth, okay? But not the case, okay? Whenever I have E to a positive exponent, that's growth. Okay, whenever I have E to a negative exponent, and by negative, I mean like a negative attached to it at the very front, that's going to be decay, okay? And so that kind of helps us deal with the fact that E is a static number, it doesn't change, but it also helps us represent both growth and decay. All right, so looking at our example, we're not going to describe the transformations here. We're just going to sketch a graph of this, e to the negative 0.75x minus 2 plus 1, labeling our intercepts and horizontal asymptote, and then just stating the domain and range. Okay, so skipping our transformations, this is decay, right? Not because of this negative, but because of this negative all the way out in front. Okay, whenever that negative is there, that's when we know e to that is a decay. This might be worth writing here that this is decay. All right, and so we know our horizontal asymptote is going to be y is equal to positive 1 in this case. And then we need to graph to find everything else, right? So let's graph. Now in Desmos, there is an e. Oh, couldn't find it for a second. There we go. There is an e. To get there, if you're using the keyboard on your iPad, you can actually just type the letter E. But if you're not using the keyboard, if you're just on the iPad, then ABC, press on that button, press on E. And it gives you the number. It recognizes it as E, right? Desmos knows what's up. And then now we go back to this display by pressing on 1, 2, 3, go to the A to the B. We have negative 0.75 left parentheses, x minus 2. Right parentheses, use the right arrow key to exit the exponent, plus 1. And there's a graph. Okay, we have a y-intercept at 5.482, and then we don't have an x-intercept because it's above the horizontal asymptote and it does not cross, right? So let's go ahead and sketch that really quick. All right, so one day I will get good at drawing straight lines on this writing tablet. That day may not come for a very long time though. Okay, I'm gonna do it down here. I think this will be enough. Okay, 1, 2, 3, 4, 5, 6. Yes, that is definitely enough. Horizontal asymptote at 1. I don't know why I'm drawing a solid line. There we go. Horizontal asymptote at 1, and I need to check to make sure that I'm actually sharing my whiteboard because I'm worried that I'm not. I am, okay. Y is equal to 1. We had a y-intercept at 5.482. 1, 2, 3, 4, 5.482 is like right here, kind of. Okay. And it's decaying, so it kind of looks like this, but better. Okay, just refer to your Desmos graph if you want a better picture. All right, and then our intercept was 0, 5.482. And there you have it. There's our nice, beautiful, darling graph. We have no x-intercept, none. Our y-intercept is that 0, 5.482. And then we can discuss our domain and range. Domain, we already know, no surprise. Range, we're starting at 1. That's our smallest y value. And then it's going off to infinity. So parentheses 1 to infinity. Okay, cool. So this is a graph involving E. All right. So E, moral of the story, weird number, just like pi, often used as the base in an exponential function. And it's also used in compound interest, right? It's kind of an unrealistic way to use it in compound interest because we would use it when we have something called compounding continuously. Okay, whenever you see this, the formula you're going to use is A is equal to P times E to the RT. Okay, P is the same, it's the principal, it's the initial value, principal. R is the rate, the interest rate. And then T is time, okay? It also can be used to model other things like population growth and whatnot. In compound interest, we don't use it that often because continuously means that we're compounding the money literally every second of every moment of every micro millisecond, right? Every nanosecond. That doesn't really happen. Banks don't really do that. So it's more often used with population growth because E kind of is a natural constant and does model continuous growth in a rabbit population, a bug population, a animal population, right? And so we'll see it in there. And so don't be surprised if you get a little bit of an application problem involving this. Okay. Hopefully that made sense to you guys. Hopefully you had fun learning about the number E. I'll see you guys in 7.4. We're going to skip 7.3, okay? Have a great rest of your day.